Okay. Yeah, 12:50. Let's start. So so many things to do, so many places to go. I'm just going to quit. I'm going to restart, and I'm going to give you a real quick overview of titration stuff. And I'll say I'll be the first to admit that some things are way far along, like say relative to nmrbox20. I mean, there are things, of course, nmrbox20 never did, like the processing. And there are things that we're moving from nmrbox20 that are already better than they were there. And there are things that are maybe in the software and are not really quite ready. I'm guilty of things being here that maybe are not as finalized as they should be, in part because that lets me demo. I'm gonna get feedback on things. So let's take a look and see how titration is. So I've started up, I just restarted to have a session nmrview or nmrfx running. I'm going to go to the file menu, and I think here what I'll do, just to show something different, under the file menu, you can open an FID, you're going to process it, you can open a data set, and if you open data set, it will immediately appear in whatever the active spectrum is. I'm going to do here open data set, no display, and that opens them so they're in memory, but they're not actually displayed yet. So let's do open data set, and then if I go to the summer workshop, Johnson, titration. Here's some nice data that I've used, examples courtesy of Kevin Gardner. And so I'm gonna just use my shift key and I can highlight all the NV files that are in that folder and say open. Okay, so we don't see anything happen because I specifically told it not to display them because I wanted to be able to open them all, control where they go. So now I'm going to go to the attributes panel, and also lets me show how this works. So in the data selector, we see on the left side all the data sets that are open. They are, I believe, sorted, so they appear in order of their name. The number is actually the concentration of the ligand that was used. I don't use that for any information here, but it's a useful way to name your data sets.
Hey, Bruce.
Yeah.
Sorry to interrupt. Right now, I want to clarify one thing. Yeah. So let's say this is great. This is an NV format because it looks like it's already you saved in nmrbox20, right?
Yes.
But if I were to start with this, let's say a Bruker data set of different experiment numbers, or even different data sets where I get the name for the different concentration of the ligand, how do you go about opening those? Is it the same method? Or?
So you could, if you had already processed Bruker 2RRs, stuff like that, you can open them directly. If you want to process them, this is one thing, unfortunately, I don't have time to show, but let me just pop it up to give you an idea. If you go to view, there's something called the scanner.
Okay.
And the scanner, if I actually, let's actually see if this works. If I go set scan directory, now I'm probably going to mess everything up, but we'll see. And go to Johnson, and I'm going to go to the ubiquitin relaxation folder and just say open, and then say scan that directory. And what it's done is this basically found every processable file in that folder.
Okay.
Folders below it. So the idea is if you had a whole series of Bruker data sets and they're all stored in 1, 2, 3, 4, you could open the folder that enclosed them, do that scan, and now you've got them all loaded. These are actually different types of experiments, so maybe not useful. But if they're all the same, you can basically, and I'm not going to demonstrate this because it's going to mess up my titration thing, but you can double click on one of them, it'll open up the FID, you set up processing on that one, and then there's a command, basically process, and it'll apply that exact same processing to every single one of them.
Okay.
So and you can actually tell it you set this output directory, and so you would create a new folder that has all the processed files in it.
Okay, that will be in .nv format, so that.
And they would, well, they would be either at .nv or .ucsf, depending on what you set up in the processor.
Okay.
Yep. But if you're going to analyze them in nmrfx, then it's probably easiest to put them in .nv. But basically either would work. So that's the idea. You could set up processing on 1, and then you can tell it to process 100. And this is useful for if you're doing metabolomics, 1D, if you're doing a series of titrations, whatever it is, set up the processing on 1 and then process them all the same.
So the scanner can scan through data set names or even experiment number. There's no restriction about that.
Yeah, it just finds things that look like Brooker, that are Brooker or Berrien data sets in there, and it will look in folders within folders within folders. Okay. With Adam's still on, as I often say, it's turtles all the way down.
Okay, awesome.
It'll, if you scan your home directory, it'll find every data set on your computer.
Oh, awesome. Thank you.
This may take a while. Okay, so let's assume that you did that. Then you could just go to that output folder and then open them all up. I have to think about exactly how they would be named. You know, I think they would all get a single name. So making sure that you had the right names. Another thing, while I'm saying that, you can actually create a text file that is a list of all the files that you want to process and read that file in, and it will then find them all, and that way you can actually assign them concentrations and things like that and process them. So that's another way. Something I really need to make some video tutorials on. So let's say we've got all those, we've got our 10 or whatever files here. I'm just going to click this arrow here, and now I've moved all the files from available to plot in this window to actually selected to plot in this window. Let's just zoom in. These have come up with colors. That's because I've actually processed already and saved these files. And for every .nv file, there can be a .par file that contains reference information that overrides what's in the .nv file itself, and color information, things like that. Well, let's see how we could have set up these colors in the first place. Let's maybe zoom in on a region here. So if I go to the Datasets tab, now I can see all the data sets that are in this window. And I can control individually the levels. If I click on one, I have a slider down here, so I could adjust the levels for each one. Offset's really relevant for 1D spectra, but we have a whole section here of colors. So it's a little subtle. This is a bad GUI design on my part. You don't know these menus are here, but almost all of these table headers have menus. So if I right click on level, there's only one menu item, which is unify, which would say set whatever levels on the first one to all of them. The color ones are more sophisticated. So if I right click on color, I can say unify, and now they all have the same color as the first one. That's not very nice. I can click on one of these color boxes and change the color of the last one, and then choose color interpolate. And now it's interpolated color from the first to the last one. Or I can choose schemes, and then I get a whole set of predefined color schemes. And I kind of like these multi-seq ones. Magma, Inferno. So if I just click on one of these, it applies that. And sometimes I find that maybe a color at the edge is a little too bright or too dark. So I've got these little sliders, so I can say, okay, I don't want quite the full scheme of that. Let's just do that range. And then click on whatever I want. So now I've assigned that color scheme to all the spectra. So that's kind of handy. There is a save button here, and this is actually a pretty important button. If I highlight all of these spectra and I click the save button, then it's going to write out those .par files. And so then the next time you reload the experiments, they'll all have that exact same whatever we set here. And it applies also to the contour level. So when I'm working on a project, often the first thing I'll do is actually get a nice view, a nice contour level for a data set. I'll set the color the way I want it, and then I'll click the save button. And then every time I reload that data set, it'll come up by default at that contour level with that color. There's a checkbox for positive or negative colors. So, maybe, for this, there are no negatives, so I really ought to, or shouldn't be. So I ought to probably turn all those off, etc. So now I've got a nice view that shows my titration starting from this deep blue or black color going to the lighter yellow color at higher ligand concentrations. So I'll just close that up. Now, under tools, there are a whole series of tools down here that I mentioned before, some of them. And what we want here is the path tool. Doesn't sound like titration, but what we really want to do is follow a path of peaks under titration. So I'm going to put up that tool. As I said, this is a fairly, you can see my little thing. I'm trying to resize this window, and because I opened up some dialogue, it froze the window size. So actually, this is kind of in progress, but coming along pretty well. So I'm going to go first to actions, and I'm going to say load titration data. And let's actually, let me open up a new window here. Let me come up here, open a terminal here, CD Summer Workshop 2020, Johnson titration, and there's a file called ligcon.txt. Very similar to what I used to use in nmrbox20, but it's a little, it's just slightly different. So what you do is, this is the name of the data set. So it has to be now, unlike NVJ, where you could sort of put part of a name on it and figure out the rest. This is the full name of the data set. The second column is the concentration of ligand. And the third column, because very often as you're doing a titration, you're diluting the protein as you add ligand. So this is the concentration of the protein, or whatever the binding compound is. That can be, I think, often I like tab separated files, but I think I automatically interpret what it is, tab or space separated. So we're going to go to actions, load titration data. I'll mention here that we also have in the same mode, we can follow pressure titration. So you have like a dataless pressure titration system. We can follow pressure titrations as well. So if we go to load titration, Johnson titration, ligand concentration.txt. I've actually fixed that error message. So we have to do one more thing. We have to peak pick the spectrum. We can't follow peak paths until we actually have peaks. So I'm just going to put up the crosshairs like we did before and click pick. And basically it's going to pick every single file, all the data sets. So let's try that again. Hopefully it'll work this time. Load titration data. Not very good at remembering where I was. Titration, ligand concentration.txt, open. Okay.
I think I missed how to get that action selector.
Right. So I got this from at the bottom of the spectrum window is this tools menu. I went to tools, peak tools.
No. Peak tools. Okay.
Yep.
Thank you.
Yep. So I've been trying to get almost everything that applies that you would do within a single or set of spectra. I've been trying to move into this tools menu and make them just so the interface is sort of similar amongst all the different tools. They all add basically bars below here. So now we have, we've loaded in the titration data. It doesn't really show us anything different, so we do one more step. So it's called the path tool because one of its features is to find paths. So let's do find paths. And let's go to the first peak. And now this is like a peak navigator here. So, oh, sorry, no, that's not a peak navigator. That's a little different. Go to all. this over here is a peak navigator. So I'm stepping, no, one more thing. I have to choose the, oh. Oh. Bruce pauses in silence. Okay, guys, apology. Quick change. You are unfortunately not going to be able to follow along. One reason I love doing these workshops is because I find problems. And last night, I found a problem and I fixed it. And I have a copy of the fixed version, but it's not pushed yet into the box. And it's basically, we made a change in the code a few weeks ago, and it changes updating all those menus of peak lists, and they're not updating when they should. So let's try this again. And like I say, you're just going to have to watch for this part, and I hope it doesn't catch us in anything else. Like I say, one great reason to do these demos is because it forces me. We have quite a few tests these days, a lot of processing tests, but especially these GUI things, not impossible, but they can get tricky to actually write a test that actually makes sure you didn't break something in it. Okay, so I'm back there. So let's do pick. Okay, so we've loaded the spectra, we've peak picked them. You can still resize, so I will. I'll come down here, peak path tool, my actions, I'll load my titration data, Johnson titration, ligand concentration, open, come over here. Now what you didn't see, I can choose kind of the list that I'm going to use for this navigator. So I can step through now different peaks. So now I'm going to come back, I'm going to do find paths. Okay, and so now the red lines are paths. So it starts at one peak, and I'm using the original colors, not my updated colors, and migrates through a path there. And I can control which peaks are actually displayed. Sometimes there's so many in a path that this lets us step through individual data sets and actually see the peak and the actual experiment that is on that peak. These pluses and minuses, I won't have a chance to demo, kind of new. There, if you're actually missing a peak, you could go in and actually add a peak and add it into that path explicitly. So I did paths, I've extended paths. That's another way to actually get more paths. And now I am even more unhappy than I was a second ago. We did load titration data. This fit button is not highlighting. Zero paths.
Hey, Bruce.
Yeah.
So in the NMR view, Jay, of this titration fitting thing, yes, there was I could generate a menu kind of, or I don't know what I remember now. It's like a dialogue where I could say, show me what is the first and last peak, and then display the path. Yes. So all those stuff Is it done where? Here?
So this is a little bit different, and some of those features I haven't added in yet. I mean, what we've got by default, it shows the first peak and it actually shows the last peak, and the first peak is shown with a box and the last peak with this cross, so you can actually distinguish them, and you can do the step through peaks, and show all peaks. You can't actually right now turn on all the peaks individually, but you can step through them. So this is in some ways better, in some ways doesn't have that. But I'm kicking myself because I tested this out yesterday and I discovered the problem that I just fixed. And why is this fit button not getting activated? Total mystery. I'm sorry. That's really weird. I cannot figure that out. Like I say, yesterday it worked. I fixed the one problem. I don't see how fixing the one problem is going to break this problem, but apparently it did. I will just summarize to you what would have happened, because it was pretty nice. It is pretty nice. As we go to each peak, we can hit this fit button and it will pop up a little panel, a little secondary window that has an XY plot that shows the titration. That's what should be popping up too. That's really mysterious. There are no error messages. So we should get a little secondary window that pops up that has an XY plot. If you hit fit, it'll do a titration curve fit to it, show you here the KD and an error bar for the KD. And basically you fit each peak and then you can add, and that will show up then in a little table in that window. So as you add multiple peaks and then you get a whole set of peaks, and then you can show the titration curves for each peak, and you can click a button in that little window that pops up that will then do a simultaneous fit, so that you fit a single KD, but different chemical shift titration values to all the peaks at the same time.
So that's very similar to that dialog box I was talking about, right? From one, so it gives you the curve plus also that like a table.
Exactly. So it's all, I've tried to keep this fairly similar to nmrbox to be kind of user friendly, and we've tried in theory to make it better, but not working at all is definitely not better. And I'm kind of baffled because, like I say, it worked yesterday, and I see no reason why. Let me just reload the titration data just to make sure that doesn't make any difference. And ligand concentration, open, find paths. I'm going to try one more thing, which is to say I'm going to create a whole new window. New window, attributes. Put all the spectra over, come to the peak selector, put all the peaks over. And come down here to show the path tool. Load titration data into this path tool. Find paths. No error messages. Well, I'm very sorry. I will kind of pronto fix this and actually post a video demo of how to use it, because it is in theory working yesterday. But that we've seen, most of what it takes to set it up. Like I say, you'll get a nice XY plot. You can fit the titration curves. You can do a plot of all those curves. You can fit as many residues as you want. Each one you click the add button and it'll save it into a table. You can select whichever ones of those in the table you want to fit simultaneously to a KD. You can export that into a text file of a table and save a vector graphics image of the table. Okay.
So Bruce, one comment on that. Again, I'm going back to nmrbox20 because that's the only one I have experience with. So the pathfinder, when it is pretty obvious that the perturbation chemical shift is clear, it catches it. But sometimes, is there like a threshold you have set where if it is not very large perturbation, it doesn't catch it?
Yeah, and I don't have time, and especially since it's not working right here, but, and I've got to document all these. So we have you notice there are 3 options here. Find paths is the first thing that's supposed to go through and find paths. There's an extend paths that will go through and try to find those even better. Something I've really messed up something here. I've definitely broken something seriously today. So we've added a couple more tools, and I find the paths in a little bit different way. There is over here, these 2 numbers here are actually tolerances that are used, kind of related to what you're talking about how far you can look to find a path. We've added these controls here, like I said, that let you step through, and basically, if it didn't find a path completely or there's missing a peak, you can go in and add a peak, explicitly add a peak to a path that wasn't there. So I've really tried to extend what's in NVJ.
I see.
Without breaking it. Okay.
And then the add button, you said is going to add more, the further peaks it is fitting, but in the lower left corner, that's like a peak navigator button.
Yeah.
Above the add.
Yes. So this is stepping us through peaks.
Peaks. Okay. Yeah.
And basically, you step through a peak, you'll see the titration in this extra window that's not popping up. That's all I can think. For some reason, that window's not popping up. If you like the look of that titration, you can click fit, explicitly fit, get error parameters. And if you really like and there's a lot of subjectivity in here. One is deciding which peaks to include and which peaks not to include in a titration.
Right.
Basically, once you've fitted and it looks like the errors are reasonable, then you'll add it, and basically then you're saving that fitted peak.
Okay, I see.
And then you can, after you've added multiple to the table, then you can do the global fit where you have a single KD to multiple titrating peaks.
So that's the workflow. Okay.
That's the basic workflow. And it's not there yet, but I've been in discussions with people at the BMRB to talk about how we actually save all this information into a star file, so that you can sort of restart and come back and have everything explicitly saved in a star file. Okay.
Thank you.
Well, serious apologies for that, folks. Let's try our luck with the next one. See what we've done there. So I'm going to quit. I'm going to restart. Okay, so there's a lot of things we can cover, but I'm going to switch completely over dynamics. I kind of hope to show you the new version of our assignment tool, but we're just not going to have time in this session to do that. So let's move on to some dynamic stuff. So I'm going to go to OpenFID. I'm going to go into Summer Workshop 2020. I think all this is going to work for your computers. I'm working on my new fixed version, but I don't know that there's anything in here that will require the fix, but we'll see. So I'm going to go into Ubiquit and relax. So we have a series of data sets in here. One was just an HSQC. 2 is, I think, a T1 or T2. So let's just open up the SER file for it. And I can see from the name HSQC T1. So this is a T1 experiment. resize that. For efficiency here, I'm just going to open up and then show you what it did. I'm going to open up the process.py file, and then let's actually look at what it did. It should be fine, and here, if you do the auto generate, should find everything properly. But let's go look at the script that it made. So operations, insert the time domain combination, and I added a TDSS to suppress the water, sign bell, zero fill, FT, phase, extract. That's dimension 1. Dimension 2, sign bell, zero fill, FT, phase. Let's go look at the script. So this data set is actually, if I were to go in and look at the Brooker files, you'd see that there's an ACQU, ACQ2S, and 3S, because this is actually a pseudo 3D data set. In fact, let's see if I can't go in and show you that. Open a terminal, sign workshop, Johnson, ubiquity, relax, because this is kind of important. Go into 2. So indeed, for those of you familiar with the Brooker files, the fact that we see an ACQU, an ACQU2, and 3 means that this is set up as a 3D experiment, but it's a pseudo 3D, and it has this VC list file. So VC list, and the nightmare of NMR is that there's 5,000 ways of doing everything. The VC list is a counter list, and it determines basically how many times you go through a loop, and that affects basically the relaxation time of the experiment. When I open up this data set, I actually find that there is a third dimension, and I find that the third dimension has the same number of entries as that VC list. And so I interpret from that it's a pseudo 3D experiment. And so that's why if you look at this processing script, there's dimension 1 and there's dimension 2, but there is no dimension 3 processing. If for some reason we hadn't detected that, we can explicitly go in and basically, had it actually added D3 processing operations, we could go in and basically remove them and get it back to being just a 2D. So what's going to happen now if we click process? It's processed that whole spectrum, and it's processed basically every plane exactly the same. So it's done 2D processing to each plane. So we do have a Z control here because this is a pseudo 3D, and we have increments here so we can step through each plane. So how do we want to analyze this? So 2 ways. So what we really want to do is get out the intensities of this peak, or this experiment. So I could just do a peak pick right now, and I would peak pick this, this single plane, because I'm on just a single displayed plane. It would actually pick it as 2D peaks. And then we can actually measure the intensity in all the other planes. But it's very common when you're doing relaxation experiments, you've actually probably already got assignments for that protein. And there's 2 ways. You might have assigned it yourself and actually have a HSQC peak list that matches this data set exactly. Or you might actually have downloaded, say, a BMRB file that has chemical shifts for that. Just real quickly, we're not going to really do that, but I want to show you that in principle, if we had gone to projects, we could open a star3 file from the BMRB. We would then have the sequence and the chemical shifts. We could go to this peak tool, and there's a simulate tab here, and we could have gone to simulate protein HSQC, selected this experiment. Actually, we should have done it on the HSQC experiment because it's a little confused because this is a 3D experiment. But basically, we would select that HSQC experiment and then generate, and we would actually generate a simulated HSQC experiment. And if our BMRB shifts were very similar, and this Andy was asking in his chat questions and just before we started, if our BMRB assignments were quite close to this, then we would have HSQC peaks that were pretty close, and we could use the tweak functionality that I showed earlier to move them into place or to individually select and do them. For this sample, I'm going to go to the peak tool, and I actually have already. I'm going to go to the open menu and come to Ubiquit and Relax. And you can see that I have saved already a t1.xpk2 file specifically for this data set. So I'm going to open that up. And I'm going to come over here to my attributes panel and say peak selector and say I want to display that T1 experiment. Okay. So now we have those peaks. So like I say, several ways. You could have pulled in another peak list from some other assignments you've done on it. You could generate a simulated list from the BMRB. That peak tool, when we do file open, it'll actually open an old .xpk file from nmrbox20. It'll open some types of Sparky files. So if you actually have assignments that you've done in Sparky, I can't remember the exact extension for the files I opened, but you can open up a Sparky file, and basically it figures out automatically. You say open and navigate to one of those files, it'll figure out what type of file it is. So any of those ways will let you load in a peak list. Now remember, this is a pseudo 3D, so as I step through, you can see those peaks, but those peaks being displayed are that single peak list. So we've only got one peak list displayed here, and we have multiple planes to fit to. So how are we going to actually measure the intensities? Let's pull up our peak tool. And we have a measure button here. And we have three things, different ways that the software gives you. And I'll show you a fourth way in a minute to measure. One is intensities. So if I measure intensities, it's going to basically look at the center of each peak and measure the intensity at each position. If I do volumes, let's actually get my selector. Let's zoom in here. If I do volumes, it's going to measure, basically sum up all the data points inside these boxes. My preferred one is actually what's called e-volumes. And why? Oh, let's see, we have one more thing we've got to do. Oh, yes. So this is a subtle but important thing. When you do that measure, it looks at the peak list and it decides what data set you should measure, because this peak inspector window is independent of this spectrum window. You don't even need to have a spectrum displayed. So the measure is actually going to measure whatever data set is associated with that peak list. And it turns out that when I saved that peak list, I had one called t1.nv, but really this data set, because the way I processed it, has this name. So I basically need under this reference tab to say this peak list is associated with this data set. And now I do my measure, I come back to peaks, and now you can see there wasn't an entry here, there were zero, a volume here. So we've got a volume plus or minus, and error bar. Those volumes are actually done for each peak on each plane. So really we have a whole set of volumes. If I go back to my peak tool here and go to this graph, you can see that for peak 0, the intensity falls in this way. And I can step through the peaks. So we're not actually going to measure, actually do the fitting in this interface right here. The kind of point of this graph is to just to let you kind of look through the data and see, yeah, it looks pretty good. We're actually getting exponential decay. It actually makes sense. So having done that measurement, we can then save out this XBK2 file, and it will save the XBK2 file, and it will save what I call an MPK for a measure file, but it'll actually have the intensities that were measured at each position. And we'll go look at that file in a second. So that's basically the gist of what we're doing. We're gonna get a peak list. We're gonna fit it to all the peaks, and then we're going to save out that measured intensity. There's yet another way to actually extract that information. If you remember, we were doing fitting before, so there is a fit planes entry here. And if I do fit planes, and let's just click it and see what breaks. Nothing broke, that's good. So what we've done in this case is we've actually done a line shape fit. Just to basically, it's at the moment it's just forced to be a Lorentzian line. So for each peak position, we have three parameters. We have a line width and a peak position, and we have an intensity. So on each plane, we're gonna fit across all the planes. So the line width and the peak position are constant across all the planes, and the intensity is allowed to vary. So that allows you, one thing it allows you, especially in areas where the peaks are overlapping, it's actually simultaneously fitting peaks that are overlapping. So you get a better resolution. The fact that you're fitting across the whole titration curve allows it to more independently extract the position of those two peaks. So that is the final way to do. Actually, there is one more way. It's still sort of experimental. You can actually, if you do fit planes exponential, it actually is fitting simultaneously the decay. So then it's actually fitting the peak position, the peak width, and the exponential decay. That method and the plotting that method relies on actually having correct relaxation delay times for these peaks. And can be a little bit tricky with these data sets. If I pull up this, I went to view, show data sets, I have this little viewer here, and it has a little button here to show the values that go along with this data set. If I go back to this VC list, you'll see that the values in the VC list are the values that are placed here. So these are actually not delay times. You need to know how the pull sequence was done and what the delays are, because these numbers need to be translated from counts into milliseconds, basically, or seconds. So you can actually go in, if you actually know those values, you can go in and actually edit this table and assign values to each row of the table to give values. There are some ways. I haven't really talked about our whole Python interface here. There are some scripts I've played with that will allow you to do that. Or you can leave it as counts, and when we get into Ring NMR, you can let Ring actually do the conversion for you. And I think that is a good place to actually move on to actually Ring, because we don't have a huge amount of time left. So any questions on that? That's basically, you know, although it took a while to display that, really the basic process you can do very quickly. Open an FID, generate or open a process file, click process, pull in a peak list, say measure, you know, if you need to fine tune it. Yes, Alexander, hand up.
I just have a a question more like a practical side. If you don't have a T1, but let's say in kind of kinetics experiment that you measure as a series of HSQC spectra as a separate 2Ds rather than a one of pseudo 3D.
Yep.
Can you combine it in a single data set to take advantage of this kind of 3D fitting?
Yeah. Yes. If we go back to this scanner I talked about,
Mm-hmm.
if I do what described of scanning the folder that has all those data sets in it, then they're actually, once you have them all loaded in here and you set up a processing script for one, there are two options. Process will actually process each individual file and save it out as a single file. Process and combine will make a pseudo ND file. So if you're doing metabonomics and you have a series of 1D files and you process and combine, you end up with a 2D file where each row is a separate data set. If you have a series of HSQCs, you end up with a pseudo 3D experiment where each plane is a separate file. So that's the way to do that. Yes, Rajan.
Bruce, so the fitting, the fitting you showed with the right click, is that the only way you do that fitting, and where does it store the data, that fit result? For example, if it uses the VC list number, I can convert that into time. In principle, I can do that, right? From the exponent, I can multiply it by my loop counter unit time.
Yeah, if it is a simple multiplication, sometimes it's actually, I know some broker sequences, it's actually a fixed offset plus a multiple, so it gets a little complicated.
Well,
let's go look at what we generate from this file. So we could do the T1 the same way, we could do the T2 the same way, we could do an NOE basically, and there is an example NOE experiment, we won't have time to do it, which is kind of it's a little trickier one because it's collected in an interleaved way, and we can actually process that again. So we have two planes, we do the measure, and what we end up with. I'm going to go to a completely different directory. I'm going to go into our the sample data directory. And here we have a ubiquitin T1. So when I saved that peak list file out, when I did the save xpk2, it will save that xpk2 file, and let's look at what's in that. Here's the t1.xpk2 file. For nmrbox20 users, there was an xpk file, and I basically this is similar but modified a little bit. Sorry, I can't get the entire thing to fold. So it's got a bit of header with information about how many dimensions there are, et cetera. And then each row is the chemical shift position of each peak and its line width and things like that, attributes. And if there are assignments. The MPK2 file, and I debate whether this made sense to put them in these two parallel files, there's some logic to it. So this actually matches exactly. So each row in this, each ID 0 corresponds to peak 0 in the other file. This is the intensities that came from the measurement. So it writes out first column, the peak ID number, the second two columns, the assignments if you had them. And then across the top are this actual file I've actually already translated, I think actually. If I didn't do any changing and just use that counter, this would be the counter number. I think this file I've actually already translated into milliseconds. But the header would be counts or milliseconds, and then each row are basically the intensities, however we measured them for each peak. So you can see the intensities falling as we go across, and then there's some replicate values that jump up. So that file, you could analyze wherever you want. You could go in, if you need to convert counts, you could go in and change this header basically to correspond to the correct numbers, however you want it.
But you did a fit on that right click menu, and if you fit it, will it store the code and
code? The fit I did, it basically, the one that I chose, when I did fit planes, it fits the intensity in each individual. It fits the line shape and width across the whole column of peaks, and it fits the intensity separately, but it's not doing this one is not doing an exponential decay.
Oh, okay. Fit
The
planes
actual
EX
intensity at
feeders.
that peak. This other one,
Yeah,
fit
that.
planes, let's see what happens. Let's do that, and then let's go look at our peak tool. It is actually written, and because the counts weren't right, it's written in this comment, actually,
Okay.
the fitted parameter, because now really we only have a single number that we fit across the whole column, that relaxation rate or time. Yep. And for that to make sense, it would depend upon having you know, the counts converted correctly in most, or as you say, if it was a linear multiplication, you could just translate this number.
But does it store that in that MPK2 file now?
That number will end up, I don't know that these files have that saved. That number it ends up in the comment field. So there is a comment column. So it would end up in the XPK2 file in the comment column.
Okay.
Okay, so we don't have a lot of time left for Ring, so let's just quit.
Okay.
And
You do okay?
hello? So I'm gonna start up Ring now. So Ring NMR GUI. Ring actually runs in like NMRFX, it runs in a command line or a GUI version. So I'm gonna start up the GUI version. You should have that installed and running on installed in your system. So in a terminal, you should just be able to type Ring NMR GUI and get this file up. I'm going to go look at a text file that we will use for this. I don't know why the colors, I hope you can see those colors. So this is a text file that we can actually handwrite, or we can build with a little GUI. We have a load setup parameters here. I don't think I'll have time to walk through that, but basically you can walk through this GUI and enter in all the stuff that ends up getting in this YAML file. Once you have one of these YAML files, they're easy to edit and change if you want to do that by hand. But let's look at what's in this file. So ignore the mall stuff. We're actually not using that at the moment. We have a fit section. For Python programmers out there, YAML is much like Python in that indentation is significant. So this fit is followed by all this indented stuff, implies that all these things are part of this fit. A file colon thing, this is basically like a hash or a dictionary in Python. So this file variable has this value. So this is an output file that we can read back in data we've already processed. The mode says what type of experiment we're doing. So this is T1, T2, or exponential decay. So exponential EXP there. We support now CPMG, R1 row, and SEST experiments at the moment. So for each experiment, you would have a different mode there. Where do we get the data from is in this section. So we're going to read a file that is that MPK2 file. It's in the format of an MPK2 file. The file basically has X values and Y values in it. And what are we going to do? Do we need to do some conversion? So the X values we're going to convert by some calculation. And this is going to be the calculation we need to do to convert the counts into delays. And so actually it turns out this is used somewhere in Brooker, so we've sort of made this usable. We're going to actually take each count, add a count of 2 at the initial value, and then multiply the counts by 0.008 to translate that into milliseconds. We could have left calc at identity, and then it would have just used whatever values you had in the header if you'd already done this conversion to start with. B0, so that it was collected on a 700 megahertz. We have a place to store temperature and pressure, although we don't use it, the nucleus that we need. So let's go open that file up. So if we go to File, Load, Project File, go into ubiquitin T1, and we can open up this project.yaml file. So just to summarize, to get here, it's really fairly quick. We did that processing, we generated the MPK2 file. We could have made this YAML file, like I say, with the setup parameters, where we would have just basically browsed, defined the value file would be the MPK2 file and the XPK2 file, and typed in any values. Some things get pre-populated, temperature and fields might get pre-populated, and some things you have to type in yourself. Once we've read that file in, then we have a plot here. Because that MPK2 file had residue numbers in it, this is a residue plot. So each number on the x-axis is the residue. If any place there's a gray bar, it means that we actually have data for it. If I click on those bars, we actually see the data values that were present. There's a bounds here, so I can auto scale if I need. So I can click on anything. I can turn on this auto scale parameter, and then I can actually click and it will auto scale for each one. We have controls here, so we can actually step through and just look at each row. Now we want to fit that. So because we put in EXP, it knows that it ought to do exponential decay fitting. So we can just say fit all. And now we've gone through and done the line fit to everything, or the exponential decay fit. If we click on any residue, now we see the fitted line. If we go over to the parameters tab here, then we see the results of the fit for this particular residue. So residue 27, 2 parameters A, and by default, we're doing a 2-parameter fit. So we have the intensity at 0 time and the relaxation rate. We calculate the fitted value, and we get error bars. The error bars come from a Monte Carlo fit, and we can actually, or Monte Carlo, basically bootstrapping. So I can go here, and here we actually see all the values that it did. So we did a specified number of fits to simulated data. So we fit the data once, got the best fit A and R value, and then we actually simulate data based on that. And we have 2 different ways. We have a so-called non-parametric way and a parametric way to fit that. And here are all the fitted values. And basically from the distribution of these values for R0 and A0, we can come up with these error bars. The error bars, you can see, are plotted on each residue. I can hold down the shift key and I can plot multiple residues. Maybe I want to look at the C-terminus tail here. I can just look at the different values. Sometimes I want them all to start at the same value, so I can hit. Where? Oh, scale data, yes. Let me redo those. Hit. And now it's going to scale to the first value, so they all start at basically at 100, so I can see the different rates at which they're decaying. So now we've got T1, T2 data fit. We can save that data out by doing save analysis. And if we'd saved it and this file had that same name, when we reloaded the file, we would actually get that analysis back in. We can export the graphics, the XY plot, to a scalable vector graphics, which you can edit, or to a PNG. We can export the residue files. We can also save these interactive charts basically in matplotlib, Python, or R format, so you could go in and edit the files and actually create your own plots, but have all the raw data to do that. So that was our T1 experiment. We can come and add a new chart, come and load a new project, and now we'll go to T2 file, open, and we'll just repeat the same thing and do a fit. So now we have T1 and T2 fitted. there's lots of other values that are displayed. So if we add a new chart, we could go in and add different types of data. If I wanted to see the root mean square, look at which values had more or less error to them, we could actually go through and find one, say, oh, this guy has kind of high error, so let's go up and look at it. Every data point that you click on will show us the actual raw data that's being used in there. And it's one of the many things I don't have time to show you, but if we started up nmrfx and opened up the data set this gave rise to, we can actually turn on a listener in nmrfx and be able to actually activate, connect to the nmrfx server. And then if I clicked on an entry here and click this show nmrfx peak, it would actually drive nmrfx to show you the actual spectral data that gave rise to that peak. So it's very easy to go through if there are unusual values to actually drill back and find what the raw data was that gave rise to that. I'll show this simulation stuff. Let's do a different experiment type in a second, but just, well, real quickly, you can see that we can simulate data with these sliders. Not so interesting for exponential decay, but it's there. While we have the exponential decay stuff, I'll say we have a lot of the low-level stuff already implemented for doing model-free type analysis, but it's not ready yet and not out in the GUI. The only real analysis we can do so far is that we can go to this correlation thing and set the results of doing the T1 analysis and the results of doing the T2 analysis, and we can estimate a correlation time for the molecule based on the T1 and T2 values.
Hi, Bruce.
Yeah.
Just kind of an obscure question, probably. So when you, let us say, this is great. And so when you go through different residues, suppose for whatever reason, a particular residue, I find a multi-exponential or a bio-exponential kind of a behavior, and you do have a way to simulate, is there a way to then say, okay, fit this particular peak for whatever crazy reason to those two T1 values or something?
Yeah, the short answer is no.
Okay.
The longer answer is we should. I'll show you in, I think what I'll do is I'm going to go on to the different type of data where different models are like the CPMG, where we tend to use more different types of models, and you can actually fit different models. We really, I mean, at the moment in the T1, T2 stuff, we really have just a two-parameter, A, B, and ABC, where C is the intensity at infinite relaxation time.
Okay.
But there's no reason we couldn't put in a multi-exponential one to let you choose from. It's in mind to be able to basically let you define an equation, but that's going to be a bit more work.
Yeah, I was about to come to the next question.
Yeah, no, that would be, I know we know how to do it in a sense in the software, but it's a bit of work to get there.
Okay.
Theoretically, we have about 5 minutes left, so I'm going to quit and I'm going to restart because I want to show you, I want to do the T1, T2 because that was a nice segue from being able to process an nmrfx. And like I say, you can very quickly go from the processing to having your T1, T2s fitted in here and look at them, and with our connection back to nmrfx to let you sort of drill back to the data and see what gave rise to different values. But let's look at some other types of experiments. So if I go to project file, and you guys have, let's actually go look and just remind you what is there for you to play with. So we have maybe next to the BPTI CPMG, we have some dihydrofolate reductase data. I don't know if we have assignments in there to interpret it. We have RNA CEST data from Qi Zhang at UNC and R1-Rho data for the same, this carbon-13 data. We have the T1 and T2 examples from Ubiquitin. There are a million different ways to do these experiments and different formats for the data, so don't hesitate. You know, I gave the demo just the other day, quick one. to Andy and some of his colleagues, and they got back to him with some data right away. And there was an issue at reading it in. It turned out fairly trivial to fix, but there are so many different ways of storing the data and stuff that I'm sure that you will find some data that we need to tweak a little bit. So let's go find the BPTI.
Bruce?
Yes.
Yes, maybe I missed this part, but I'm just wondering where this project that gaming come from. So how you generate from the
How we generate which?
the input for this file, for this Ring software.
Yeah. So that's one of the biggest challenges, actually handling all the different data formats. So in these examples I have, the ubiquitin examples are these MPK2 files as generated in nmrfx. And you could pretty much, you know, if you had anything else generate these intensities, it would be very easy to put it into this format. It's very simple. The BPTI data that I'm going to show you now, it's actually in yet another format, and I think we've got most of these documented. This is actually, these are actually relaxation times and error bars for each one. The RNA CEST data, in this case, it's a file for each individual residue, and so we have an offset. The CEST saturation was done at, the intensity that was measured when the saturation was done at that point, and an error value. So we've got a variety of examples, and it shouldn't be hard to, you know, if you're not in that format, to sort of convert into one of these ones that we can read. And, you know, if you have trouble, like say, you know, somebody had trouble last week, they sent me a file in about 5 minutes. I figured out what the problem was, and some of it we could just tell them to change in the YAML file, and some I had to actually tweak the code. But that's the only way we're going to get this right, is with more people sending us more examples.
Okay, thanks.
So this now is CPMG data. And we do the same thing. Again, I read it in the file. This is a residue across the bottom. The gray bars imply that there's data. So again, we tried to make one program that basically does different analyses, but has a common user interface. So now we've done fit all. We scan across all the residues. The data for each residue we've fit to basically 3 models. If I click on one of these guys, I can choose these. So a no exchange model, basically there's no exchange. A CPMG fast model, CPMG, the full Carver-Richards model. And we use this AIC, Yaki, I always probably mispronounce information criteria to decide which one is the best explanation for the data. You only see a green bar if one of the 2 models besides no exchange was true. So everything has a gray bar. Basically, if I click on it, you'll see they're basically more or less flat lines. There's no evidence of exchange there. But if I click on a green bar, you can see the classic CPMG shaped curve. And some of them, it fit to CPMG fast model. I think over here, let's go to my auto scale bounds. You can see this has the characteristic, more complicated structure that is only explained in the slow exchange model. So it was fit to that. Now, the whole point of doing NMR dynamics is to make some correlation back to the molecular structure and what it's doing. So it's one thing we've added is the ability to show secondary structure on here. So I'm going to load, we have a simple text file, and you have all this data, so you can see that format. So now we've got a plot of basically sheet and helix, and these lines interconnect disulfide bonds. So you can see there's a group of residues that exchange at each end of this red line for this disulfide. And so presumably that's a disulfide bond isomerization, and the exchange is happening with the same exchange rate, we presume. So we can go in and select all these residues, auto scale, so we can see them all. And then instead of say fit all, we could say fit selected. And now it's going to do a simultaneous or global fit to all those values to a common exchange rate. So if I click here, you can see that we have individual delta ppm values for how much the chemical shift changed between the ground and excited state, and a common exchange rate for all the residues, and a common population. So 95% in the ground state and 5% in the V state. So pretty simple to do that. As I said, there's a whole simulation tool here. So in terms of educational purposes, you can go into the simulator without even having any data. And so you can actually say, well, what is R2? Well, that's the apparent relaxation rate at infinite in the CPMG field strength for the absence of exchange. What happens as I change the exchange rate? What happens as I change the population of the curve? What happens as I change the chemical shift difference between the two states? So that, let's just show you one more curve, and then theoretically we're done. Ring NMR GUI. I didn't actually have to leave. There is a clear project, but sometimes doing demos, it's safest just to get out and restart. So let's do one more experiment. Let's go to project file. And for any RNA people out there, here's the CEST data. And what I want to show here in particular is that we have a million different models to fit to. Is there a question? No. Under preferences, there's sections for CEST equations, and so we've got quite a few. And we actually have a publication submitted on Ring that actually sort of documents our experience with how the different ones fit. The ones that are not labeled exact are approximations, and they're much faster. So by if I'm just doing exploratory work, I might just leave Trot Palmer on, which works very well, and then just do fit all, and it's going to go through and do a fit. Once I sort of scale down to what I want to look at, the exact one model is doing an exact fit to the Bloch-McConnell equations. And oops. The slowest thing about all this analysis is how many of these bootstrap samples we do to get the error bars. So I'm just going to set that down to a smaller number, and then it will run a little bit quicker. And let's highlight the two residues and say fit selected. While it's processing, you're going to see this start processing down here. If it takes forever and you want to change something, there is a halt button up there. Okay, but not too bad. So it's done. So now we've done a simultaneous fit to the chemical shifts at two residues across 3 different saturation values. And you can see very nice fit. Go over to our parameters table here and sort KEX, so about 109 per second. So there you go. That's kind of a very quick intro to Ring, and I really encourage people to just start up Ring, and you can go to each of those examples and load in that YAML file and see how it works. Look at the YAML files to see what's in them, what you have to do. I'm sorry we didn't walk through this whole setting up parameters thing that actually lets you build a YAML file, but it's fairly straightforward. There is actually, to see the documentation for this, you really need to go, failed to, let's go to Mozilla, and I need to do advertisement here and say all of Ring is developed under the auspices of the Center on Macromolecular Dynamics by NMR. Art Palmer's a PI, and and McDermott and I are co-PIs. If you go to dissemination software, you can download it. Again, Ring is built just like NMRFX. It's a Java-based program. You can download and run it on your Mac, on your Windows, on Linux, or the latest version is in the box. There's a PDF file for documentation, and all that sample data is available on the site there. And there is an introductory, introductory tutorial. It just does not seem to be running. Okay, that's good to know. There will be back soon. I think that's available on a different page as well. So maybe let's try there. Tutorials, video tutorials. No, something's broken on the website. Okay, that technically is the schedule, but I still have some iced coffee in my coffee cup, so I'm good to hang around. And if people actually want to, do more hands-on stuff or go back and revisit any of the stuff that we talked about earlier, I'm happy to do that.